Hey everyone, did you know microbes change their shape to support their survival? Did you know microbes can damage antibodies, making them dysfunctional? Or attack their microbial enemies? Or worse yet, mimic antibodies to your body? The purpose of the immune system is simple: cure or prevent disease. Macrophages and their precursors, monocytes, are the big eaters of the immune system. These cells reside in every tissue of the body, albeit in different guises, such as microglia, Kupffer cells, and osteoclasts, where they engulf pathogens and cells undergoing programmed cell death, which is also known as apoptosis. They also produce immune effector molecules known as cytokines and chemokines. Macrophages are the first line of defense against pathogens, and the mode of their activation will determine the success or failure of the response to the pathogenic aggression. Macrophages are remarkably plastic and can change their functional composition and shape depending on the environmental cues they receive from chemokines and cytokines. Macrophages are hypersensitive to hyperoxia when lacking control by chemokines. Through their ability to clear pathogens and instruct other immune cells, these cells have a central role in protecting the host but also contribute to the pathogenesis of inflammatory and degenerative diseases. Substances typical of bacteria, which surround the microbe like a cloud, attract macrophages, whose job it is to devour such intruders. As soon as the immune cells detect the intruder, they cover the bacterium with part of their own cell membrane like a hood called a phagosome, creating a membrane sac in which the intruder is trapped. This sac cuts itself off into the inside of the macrophage and is now the point on which all of the macrophage's offensive weaponry is concentrated. The sac is flooded with oxygen radicals and acid. Another kind of membrane bag filled with lysosomes merges with the phagosome sac and confronts the microbe with highly reactive digestive enzymes. A few hours after the first alarm bells have been rung, there is nothing left of the bacterium and the potential danger has been eliminated. This is what happens in a healthy immune system. However, a whole range of pathogens have become specialized this very part of the defense mechanism and survive and even multiply in these macrophages, which are actually supposed to kill them. Some bacteria can subvert this defense mechanism and even multiply within the macrophages. One of these pathogens is mycoplasma. The mycoplasma are able to prevent the phagosome development inside the macrophage, preventing acidification and merging with the lysosomes. As a result, the bacteria are not exposed to a large array of the lysosomal digestive enzymes and acid. Basically, what this means is that the mycoplasma manipulate the macrophage. They make themselves comfortable in an environment free of acid and digestive enzymes and multiply there. Within a few days after the onset of the infection, the macrophage dies of the infection, they disintegrate, and they release the multiplied pathogens. Cell biologists have demonstrated that this death is necrotic. This means that the cell components escape, attract other immune cells, activating them. Ultimately, the result is inflammation and tissue damage. It is quite possible that the mycoplasma do not really mind this, since they can then grab a passing macrophage and colonize fresh material. The death of the macrophage contributes to the mucosal inflammation by causing the release of the preformed pro-inflammatory cytokines, such as interleukin-1. In addition, the loss of the activated macrophage is likely to decrease the effective immune response to the pathogen. This limits the inflammation and would contribute to the inability of the host to eliminate the infection from not only mycoplasma, but from other microbes as well. Tissue repair is also inhibited as the macrophages go through apoptosis. Numerous effector cells can induce apoptosis of macrophages, including nitric oxide from arginine supplementation. H. pylori increases INOS production, causing apoptosis in macrophages. Hyperresponsive activated macrophages can cause tissue damage and destruction and autoimmunity. Toxic shock occurs in worst-case scenarios. Autoimmunity is caused by an initial hyperinflammatory response followed by a state of profound immune suppression. Overactive macrophages can promote fibrosis, hypertrophy of tissues, and exacerbate cytotoxicity and allergic responses. False positive and negative antibody responses take place with chronic overactivation. Chronically activated macrophages are unable to transition to a regulatory state and consequently continue to produce inflammatory cytokines. Underactive or deficient macrophages are unable to clear damaged tissue, failing antibody recognition, continued production of inflammatory cytokines and chemokines without control, and eventually cancer or sepsis. In severe responses, septic shock occurs. Similarly, uncontrolled activation of the regulatory macrophages can contribute to the progression of hyperplasia, and by releasing interleukin-10 can predispose the host to infection. Failure to control inflammatory macrophage activation responses can lead to pathologic diseases. The hyperproduction of macrophage-derived inflammatory cytokines leads to vascular and tissue destruction, multiple organ dysfunction, chronic illness, and autoimmunity.